Hello, this is lesson number 2. We're going to start with chapter 9, which is about stresses and strains. So statics and strength of materials. So statics is the study of forces and force systems acting on rigid bodies at rest, whereas strength of materials is the study of the relationships between the external forces acting on elastic bodies and the internal stresses and strains that are generated by these forces. So you need to know something about statics to be able to study strength of material. Let's take, for example, a metal bar that's loaded with force P. If we were taking the free body diagram from segment B to A, we notice through the principle of transmissibility that we have P1 acting on the ends of that bar. Consequently, the other way around, we can look at it if the load was reversed and we're talking about a compressive force. Okay. So, what stress is either we're going to call this direct stress. Direct stress is because the force is normal or perpendicular to the section. Okay, so direct stress. Sigma equals that force divided by the area. So really what happens is when you apply the load to the bar, what's happening is that the internal material of the bar is resisting those forces, and then hence we're stuck with stress. I'm going to use a term called allowable stress. And I'm going to talk about that in a little bit, but we can calculate the force that's allowed based on the allowable stress, or if we have a problem where we have to figure out what the area is for an allowable stress, we can also use this equation right here. But again, it's the same equation. We rewrote it a couple times. So allowable stress, that's a term we use in analysis problems where a member must support a given load without exceeding a certain stress level. That's hence the allowable stress. Another term I want to throw at you is bearing stress. Bearing stress is really a compressive stress that is exerted on a body due to contact with another body. And then let's talk about shear stresses. So shear stresses, unlike normal stresses, shear stresses are developed in a direction parallel to the surface on which the force acts. So that's a shear stress. So in this particular case, we have a block that's sitting on or bonded to a plate. Okay, and when we apply a force P to the block, what we're doing is we're creating a shear stress along this plane A, B, C, D. That's a shear stress along that plane. Okay, so in this particular case, let's keep talking about shear. We have these two plates that are glued together, and we're going to apply a tensile load to the ends of the two plates. So what happens here is a tensile force is applied to the two plates glued together. The glued surface is subject to a shearing stress. Okay, so essentially that would be this area here that's represented by the area of the two plates that are in contact and glued together, and that is the shear area. Or another case of shear stress is we have this body here, this block. It's up against a rigid support, and I got this load P pushing on this case. So in this case, I have a solid member here, but I have a shear plane from A to B, where this rigid support only backs up the lower half of this block, which means that this separation plane AB, a shearing stress is applied to that plane. Okay, another good example of shearing stress is a punching operation. Okay, so in which case we got a plate here and a punch and then a die here on the bottom. Okay, when the force is applied, what is the force it takes to make this blank? So essentially what you're doing by punching a hole is you're making a blank. So the shear area is essentially the thickness of the plate times the circumference of the disc. Okay, so this, you think of it this way, this area around the whole outside of this slug is the shear area. So the shearing stress would be the force P divided by the shear area. So let's talk a little bit about strain, axial strain, and deformation. Okay, so when a body is subjected to a tensile or compressive load, it will deform. Okay, so strain is a dimensionless quantity. You can just look at the units here. The total deformation is in inches, and the original length is in inches too. So essentially, strain is dimensionless. It's inch per inch. We're going to use this Greek delta here to designate deformation, and then this is the overall length. So essentially, when you're applying a load to a bar, it is going to stretch. Okay, and it's the same with shearing. Okay, so you apply an axial load to a bar, it's in tension, it's going to stretch. But if you give a shearing load to this member here, this motor mount, it's actually going to shear. You're going to have some shear deformation as well. So it's essentially the same type of action. Let's talk about Hooke's law. Okay, we all know about the modulus of elasticity. So we have stress and strain on a curve here. So the stress divided by the deformation at point A is also equals the stress divided by the strain at point B, and that's a constant, and that's E, which is stress divided by strain, which is our modulus of elasticity. Okay, so for most engineering materials, shear stress and shear strain are similarly, let me get you one right here. For most engineering materials, stress and strain are proportional up to the proportional limit. And then the modulus of elasticity, namely Young's modulus, that's the proportional constant of the material. If you want to see what a bunch of different materials are listed in Appendix G, if you want to see what the modulus of elasticity is for a bunch of different materials. For steel, we're going to use 30,000 psi for modulus of elasticity for steel in this textbook. Now shear is similar. Okay, instead of the modulus of elasticity, we're going to have the modulus of rigidity. That's the proportional constant of a material. Again, you can see those in Appendix G. And then for modulus of rigidity, we use the symbol G. And for steel, in this textbook, use 12 million psi. Okay, here's another handy equation for us to use. If we know our modulus of elasticity is stress divided by strain, and then we put in the equations for those two, we end up with this equation, PL over A delta. Now, when we solve for delta, we get PL over AE. Okay, so if we know what the load is on a material, and we know what the modulus of elasticity is, then we can calculate what deformation is at any load using this formula. I'm going to stop right here, and we're going to pick it up in part 2 of lesson 2.